Let's consider an inductor in an AC circuit as such. So we have a AC source, and at an instant, say we have a current of I, and the voltage across the inductor of inductance L is, say, VL. So here the agenda is to understand how I varies, how I behaves. Let me put it in this way, in a simpler language. That's our aim. How I behaves as E varies, right? As the voltage varies. So that's our aim over here. Now, when I switch it on, all of this is happening. So let's apply Kirchhoff's law. So we know that the sum of voltage that we can consider across a loop should be equal to 0. So we have E naught sine omega t, that's the source. Then we have the inductor that behaves in this way, right? So if you think about it, this makes sense. When I increase the voltage, just a second, my bad. So when I increase the voltage, okay, I can't. Yeah, not able to do that. Okay, let me come back here itself. So when I increase the voltage, what happens? This di by dt increases. So as a whole, this and this together will give us 0. When this is tries to drop and all of that, this value becomes negative. So overall this becomes positive, and that again becomes 0, right? If you think about it, the maths works out actually. Oh, I was raising something else. So omega t minus L di by dt. This is for assuming inductor has negligible resistance. Okay, so we are trying to figure out the expression for I. So next step is expression for I. So what will I do is I'll rearrange, right? And we'll end up with E naught sine omega t sending to, say, right hand side. And then we have dt in the numerator and L that goes to the denominator. So to find the entirety, right, entire effect, what will I do? I'll integrate. So integrating, I want the net effect, so net expression. So E naught by L is a constant. Sine omega t is what I have to figure out. And when I do integrate this, what will I end up with? E naught by L integration of sine omega t is cos omega t minus divided by omega plus a constant. But this constant c, it goes to 0. Okay, let me write it as c itself. That would be 0. Because it's a sinusoidal wave, it will average out to 0. Okay, guys. Now, we have I, which is equal to E naught by L omega. Funda here is we need to compare it with this. So the cos function will not help. We have to convert it into sine function. So minus sine of 90 minus theta. Right? I hope you guys remember this. So this is your outer bracket. So sine 90 minus theta is cos theta. So using that, I've written this. And again, we have a negative over here. So let's also, and I'm calling this as I naught. Then we have this to be sine of omega t minus 90. So some of you might be confused. So I'm writing it over here. So we use two things. Sine 90 minus theta is cos theta, and sine of minus say alpha is minus sine alpha. So this will come under your 11th grade basics trigonometry. So that's where you guys can revise. If you are not able to understand this, that's what you can do. Now, when I compare it with this, what can I conclude? So on comparing E naught and I naught, those are constants, sine omega t, sine function. Okay. So this has to be compared with this, right? Sine and sine, we can compare this expression. So what is it telling? Our E, which varies as a function in this manner, right? I, which varies, which is a function of time in this manner. So this is an expression which is nothing but pi by 2 over here. So current as a whole is lagging, or it's waiting for the voltage, something to happen to the voltage, and then the current changes. It's always slower. Does it make sense? It's always slower. That's what the conclusion is about. So again, understand the main agenda, then the derivation will make sense. Mathematically, it's not that difficult, but I want you guys to understand it. There is part 2 wherein we'll understand it a bit more deeply, but I would want you guys to catch up whatever you guys can over here. So the main agenda here is to understand how will the current vary in a circuit which has an inductor and an AC source. So as in when you change the voltage, that's what is happening over here. What happens to the current? It looks like as if the current is kind of lagging behind it, right? When you compare this to expression, we can tell that the current is lagging behind. It's kind of trying to catch up. It's reacting. So we can term it's reacting, right? When you look at your phasor diagram, it would be so. If you look at it carefully, let me kind of pause it. The red line indicates your voltage and the blue line your current. So the red line is leading while the blue line is following. Can you see that? Now, when you look at your sinusoidal graph, the point wherein we have the maximum, right? Look at the points of maximum. You take up any maximum as of now, at this instant, take up any maximum of red. Look at where is blue. Is it to the right or left? It's to the right, right? So it is delayed. The response is delayed. Even with your phasor diagram, we can see that red line is at the peak, while the blue line is 0. If you look at the projection, let me just unpause for a second. Can you see that? Right? The projection of the red was maximum, while the blue was minimum. It was 0 actually. Now it's a bit more than 0, but you got the funda, right? So the current is catching up to the voltage. It's responding to the voltage. That actually suits the behavior of an inductor. It responds to the voltage variation. It does not have its own characteristics, as in own source per se, own storage per se. Right? Actually, I should not be telling that storage, but yeah, it is responding, it's reacting. And that behavior is seen over here, as simple as that. Right? So I have written a text over here regarding why the constant is 0. This you guys have to write in exam. So in AC circuit, the current and the voltage are sinusoidal and have no DC component. This means that the average value of the current over a complete cycle must be 0. The average value of cos theta over one period is 0. So the constant must be 0 to ensure that the current purely is sinusoidal. So it's a sine wave, it has to be 0 is what it means. Okay, now let's look at the graph per se. So we have the current voltage versus omega t. So let me do it properly. It would be something like this. Agree? So we have a gap of 4, almost correct. If that is a graph representing voltage, so this will be 0. This point will be pi by 2. This will be pi. And this will be 2, 3 pi by 2. And this will be 2 pi. So next the question is, how will the current be? Current is lagging. That is, whenever you have your maximum in voltage, the current will be there 0. That's where it starts in some sense. So, and then it reaches maximum at pi. And then here, sorry, not there. So it will be, okay, not that. This is also wrong. Yeah, maximum over here. So when the voltage becomes 0, this is maximum, and so on and so forth. This is the basic behavior. There is a gap of something like that. So this is somewhere amplitude is this, right? Okay, that would be a complete graph. So this point is your maximum, or pi by 2, comma E naught, while this point is your pi, comma I naught. This is the entire funda. Okay, so if the current is, or voltage is somewhere over here, that's our E naught, then at a difference of pi by 2 is your I naught. Okay, so say this is omega t, and this will be lagging behind that, omega t minus 90. So this is the entire funda, guys. So this point is your E, instantaneous voltage, and that's your current. That's your origin. So this is the entire funda. So basically, we are trying to tell that the inductor is responsive in some sense. It will respond to the situation. Okay, that's the basic nature, right? Conclusion. The phase relationship between your voltage and current is such that the voltage is ahead of current by an angle of 90 degree. That's it. While in your resistor, purely resistive circuit, what happened? They were in phase, as in when you change the voltage, quickly the current in the circuit, entire circuit responded. There's no delay. But here there is a delay in response. That's it, right? So something like this. Okay, and now you guys can have a look.